Hi, everyone. Welcome to episode number 2 of Deep Papers, where we interview AI scientists and deep dives on AI research and AI papers. In today's episode, we are going to be interviewing Tri Dao and Dan Fu, who are computer science graduate students at Stanford, the authors behind the H3 paper, Hungry Hippos, which is a novel language modeling architecture that on a variety of tasks performs similarly, if not better, to transformers, but has very impressive context length scaling properties such that it admits very, very long context length if desired. So that's the episode for today. Before we begin, maybe we can just go around and do really quick intros for everyone else on the call. I'll start. I'm Brian. I run a Twitter account called AI Pub. Cover AI news, AI media, AI research for primarily technical audience of software engineers, machine learning engineers, and machine learning researchers. I also run the AI Pub Talent Network, which is basically a referral program for software engineers, ML engineers, and ML researchers. Sign up. I'll refer you to really cool AI startups if you're looking for your next gig.
Great. I'm Jason from Arize AI ML Observability.
Hey, Aparna, also from Arize AI ML Observability.
I'm Dan. I'm a PhD student at Stanford. Oh, I think Tri and I are okay. Yeah.
Hi, I'm Tri. I'm also a PhD student at Stanford. We're in the same lab. Yep.
Yeah. So I'm a PhD student at Stanford. We're in the same lab. We work with Chris Ray, broadly interested in systems and machine learning, long context, as Brian mentioned. Very, very happy to talk about all those things today.
Yeah, and thanks to Jason and Aparna and Brian for inviting us to this chat. We're really excited.
The honor is ours. I've heard it's a very weird term to hear over and over again at events and parties and talking to researchers, but I've heard Hungry Hippos over and over and over again for the last couple of weeks. So it's great to chat. Let's get started. The first question I have is basically like, what's your 1-minute elevator pitch for the paper for those who are listening? What are maybe the major problems that you guys address, and what are the major contributions or cool results that you guys came up with?
Yeah. So if you kind of take a very high level view, there's a couple of things that we're very interested in. So in H3, we were looking kind of at language modeling, and language models these days have kind of one major bottleneck that we wanted to address, which is they really struggle to capture long context. And that's due to a very kind of fundamental technical reason in the architectures that people are using these days. They're all using this thing called attention, which I'm sure many people on the call have heard about. But attention has this property that it scales quadratically in the sequence length. So in H3, we wanted to see, okay, can we replace attention with something else? And our lab has been working on these primitives called Statespace Models for a couple years now. So we wanted to see, can we use Statespace Models in language modeling? There were some more technical challenges, which I'm sure we'll have time to get into, basically having to do with, can you kind of compare words in a sentence, like the word at the beginning of the sentence to the word at the end, to try to kind of do some semantic reasoning. And we found that kind of once you solve that problem, you can use state-space models in language modeling, and then you can go to very long sequences without scaling quadratically.
Very cool.
So, and one challenge that we run into is, as Dan mentioned, is the expressiveness problem, but the other problem is kind of efficiency. Like, how do you actually make these things efficient? Because transformer attention came out 5-6 years ago. Tons and tons of engineers and researchers have been optimizing attention, and we've also worked on optimizing attention. So with a new model, we had to put in some work to make sure that it runs at least as fast as attention on modern hardware. So we tackle both expressiveness and efficiency. And in the end, I think it worked out pretty well. We have something that up to some scale, does about as well as transformers. So that seems really promising. And as Brian mentioned, maybe we'll be able to scale to longer sequences and hopefully get better models that way.
It'd be great to, I feel like not everyone knows what a state space model is. Even starting there at the highest level, feels like you borrow from linear time invariant systems, but love to just hear, what is it? How is it different? How's it different or new versus what's been done out there?
Yeah. So actually, state space are actually, as you mentioned, very old concepts from control theory back in 1960s, I think, from Kalman. So if you heard of Kalman filter, that's the state space. So more recently, people have been putting these things in deep learning. So the way they work is you can view them as kind of a linear RNN, so a recurrent neural net, but there's no non-linearity. So that's one way to view them. The other way to view them is a really long convolution where you're convolving with something that's as long as the sequence length. And then, he has some more recent stuff leveraging this connection. So, folks in the lab like Albert and Curran has been pushing on this direction, and they made really exciting, progress, I think, in the last couple of years. So things like, the S4 model seem to be doing really great at some of these long range, benchmark tests. So, we are excited to take that, architecture and put it in things like language modeling, which requires a little bit of a twist. So I think the high level take is that these state space models are actually quite old. They kind of look like either linear RNN or long convolution. And now we're kind of trying to figure out how to put them kind of on par with attention in the realm of language modeling.
And I was going to ask, can you also just kind of like the intro you gave to SSMs, can you give a quick brief intro to attention and kind of what you were starting to compare SSMs with?
For sure. Yeah. So attention, I think, was started in 2014. Folks from, Benjo Lab were using this in NLP. Basically, you given a token, you kind of compare it against other tokens in the same sequence. So they were using it in the context of actually recurrent neural nets. So back then, RNN, LSTM, things like that were all the rage. And so I think in 2017, folks at Google figure out that, hey, you actually don't need all this recurrent stuff. And if you stack a bunch of attention layers and MLP layers, they actually do really, really well. And they parallelize really well. So that's the problem they tackle, is that these things parallelize really well on hardware. And so they can scale these things up and train really well. And that has kind of taken over machine learning. Like right now, I think in all applications, like transformer and attention are what's powering all of these exciting applications. Things like ChatGPT, things like AlphaFold, things like Stable Diffusion, has enabled a bunch of really exciting progress. So we're really happy to be in machine learning right now because there's so much excitement.
I was just to go on the state space models kind of line of conversation. I was curious if you could also comment just a little bit on both your guys's and maybe your lab's background with state space models. And also, like, kind of, you mentioned the paper. First off, you guys have been working on these for a while. Second, something that's new to me, is, not the most knowledgeable AI researcher, but I didn't know that they've actually they've been used in a lot of other contexts recently. You mentioned this in the paper that, if I remember correctly, they're used in some state-of-the-art context for audio generation or something like that. So if you could also comment maybe just a little bit about how state space models are being used now. Curious about that.
Yeah. So, as Tree mentioned, a couple of our lab mates have really been exploring their use cases for a couple of years now, like Albert and Curran. So I think originally when they put out the S4 paper in 2021, I think that was one of the first demonstrations that state space models can really work well in long sequences. And there are some of the use cases where kind of speech understanding, like if I say a word, can you understand what word it is? There were some kind of long range tasks that go many times longer than your typical transformers. After the S4 paper, Kurt and Albert put a lot of effort into kind of doing speech generation. Kind of one intuition is that a state-space model is kind of a good model for kind of audio waveforms. And because of that, you can kind of use a state-space model to model audio waveforms. They have these nice demos where they can get a machine to kind of count from 1 to 10 with kind of no priors. And if you listen to the bass lines, it's really remarkable how transformers are kind of really struggling to do this. Since then, we've had lab mates kind of do time series forecasting. There's kind of like a electricity forecasting, that type of thing. I think weather forecasting a little bit, and things of that nature. So people were really using it a lot for kind of time series, continuous signals, and things like that.
The amazing thing is that these ideas, even though they're we now a bunch of folks from different places are using these things. I think like when it first came out, it looked a little bit mysterious, but people have been figuring out and simplifying these things. So folks at IBM kind of simplify these things. Folks at MIT are using it in, like, I think in RL as well. So a bunch of places they're using it in video generation and so on. So these ideas, I think we're seeing some of the impact in a few applications done by a bunch of other people in the field as well. So this is this is really great. Like we're seeing people adopting this stuff, and I think that making a progress towards addressing the long range context, learning, modeling long sequences, like that's the stuff that we're really, really excited about.
Just really quick, just follow-up question on that. Like super high level, why are state space models so good at doing long context stuff? I mean, you mentioned in the paper the fast Fourier transform. Is that the main reason? Are there other reasons? But like, why are they so good at that?
I think there's you can kind of look. Oh, good. Oh yeah, I think there's maybe two ways to look at it. So one, just from a efficiency standpoint. So Tree mentioned that one way of looking at these state space models is that you can look at them as just a very long convolution over the sequence. And there's this theorem from the signal processing literature called the FFT convolution theorem. And it basically says that you can compute a very long convolution using the FFT. And the FFT it's another one of those algorithms that is decades old, and people have been thinking about it, working on it for a long time. So and it has a property they can compute it in almost linear time. So just from the kind of a computational standpoint, you can just use much longer sequence. You can just like feed them in a lot longer. From a more theoretical standpoint around the actual architecture, what it's doing, there's a lot of interesting, rich theory about how this representation can kind of remember the entire sequence and kind of take information from the whole sequence depending on what you need. So there's sort of these fundamental reasons that you can that you sort of have very long memory. Then there's also just these efficiency reasons for kind of just being able to process long sequences.
Dan, just a super simple question. Can you give me an example of a long range task that an SSM would do much better than a transformer on?
Yeah, so a very simple one that I think a lot of people will sort of understand is audio processing. So if you imagine your audio waveform, these things will be sampled at like 64 kilohertz or something. So that means that in 1 second of audio, you have 64,000 audio points. If you try to feed this into a transformer, you need 64,000 squared different computations in order to do that. and now you've blown out your GPU memory. You can't load your model. Your CUDA is going to complain. NVIDIA SMI is going to say, "Oh, I can't do that anymore." With an SSM, not only can you process it, you also have a chance of actually kind of modeling kind of how the audio waveform changes over time, and that's one example of something that SSMs have shown a lot more power over than transformers.
And you have some examples in your paper of maybe a very specific long range task like recall. Can you describe again, like not everyone knows the long range task problems or the simple things where things fall over, but what's an example of a long range task like recall that you tested against? And and maybe also describe some of the data sets out there people are testing against.
Yeah, so in H3, we were kind of very interested in language modeling. So there's kind of a few ways that you can look at it. So the task that you mentioned, Jason, recall. So that one is really, let me give you an example sentence. So if you have a sentence like President Obama went to the park with his dogs and met Michelle blank. And the question is, okay, what is the word that is going to come after Michelle? Is it Michelle Bachmann? Is it, I can't think of other Michelles off the top of my head. But we kind of, as humans, we know that the answer is going to be Michelle Obama, because at the beginning of the sentence, we were talking about President Obama. And so that is an example of one of the tests that we were looking at. So there's a token, so kind of at the beginning of your sentence and kind of near the end of the sentence, can you still remember it? Can you recall it? Hence the name, recall. And that's one example, that's one of the tests that we were looking at. In our paper, we actually found that SSMs could not sort of immediately do that recall. And the reason is a little bit interesting. So if you one way to look at attention is you're going to be kind of making comparisons across your entire sequence, and that's kind of why it's quadratic. So if you get to the end, you see Michelle, you're going to be like, okay, there's a bunch of different words that can come after Michelle. Let me go one by one with every single word in my sentence. Okay, president, Michelle president, maybe not. Michelle Obama, sounds right. But then I'm going to keep looking at Michelle Park, Michelle Dog, Michelle, I'm forgetting the rest of the words in the sentence already. So attention can kind of do it by brute forcing it and kind of saying, okay, I'm going to go look one at a time at each word. With a state-space model, what we were able to do is we were able to kind of encode a little bit. Hey, maybe there's a concept that you should remember throughout the whole sequence. Maybe this president or this Obama word. Like if you think about the sentence, the words that you probably remember are President Obama, maybe something about a dog, maybe something about a park. But there's a bunch of words in the middle like, I'm pretty sure I said walk, but I can't remember anymore. So one intuition is that the state-space model is saying, okay, we can have a model of what to remember from the sentence so that you can recall it at the end.
Yeah, so just to add to that, and Jason, you were asking about tasks. So I think those are some more of the more academic tasks. I think right now there are a bunch of applications that would benefit from this kind of long range interaction. So one is obviously ChatGPT, right? So when ChatGPT came out, I think one feature that OpenAI advertised that it has great memory. So it can remember stuff that it was talking about, pages ago, right? So that's something that for attention right now, we're kind of brute forcing it. We just like extend the context length. As you mentioned, we just compare against all the words that came before. And so the context length, I think, can get to 4,000 now. Even though these models are really large, the context length is actually not that large, only 4,000. We've talked to folks who are doing things like code generation. Like you're editing a file and can it suggest things that are from a completely different file in the same directory or from different directories or from the library that you're importing, right? So somehow it has to remember what's in a library or from in different files. So I think there are a bunch of really new AI applications nowadays that could benefit from this long context. And this is why this is an area that we want to make progress on.
Yeah. So my question is like, where did where did that come from, and why is it hungry?
Sri, I think you should. I think you should take this one.
Right. Yeah. So we had a paper a while ago called Hippo. This is me and Albert, and of course Chris and some folks in the lab. We call it Hippo because we were doing things like memory. We were trying to figure out an explicit memory mechanism for these models. And so we were just brainstorming names, and we come up with like memory, hippocampus. So what if we call it Hippo and see if the reviewers are going to figure out if it means hippocampus. And then we had a logo that's this cute hippo. And so some of the more recent Statespace models are based on that concept, like explicit memory. And so we want to do another one. And we're just brainstorming, and of course Chris came up with this great idea that, hey, what if we call it Hungry Hippos? And why are the hippos so hungry? So that's like that's left to us to figure out. So yeah, I thought we were just playing around.
Very cool. I just wanted to ask just a little bit on kind of like maybe some of the high level ideas. And you mentioned a little bit of this already, but what are maybe some of the high level ideas behind this H3 layer? And I'm also curious, like how did in particular what's novel about this work? Because you do mention like other people have been using state space models to do this kind of stuff, but obviously they haven't been able to perform as well on various language benchmarks. So I'm kind of curious, like what are maybe some of the new key ingredients that you guys found and added that made these work so well?
Yeah. So part of this answer will kind of explain why it's a hungry hippo and not just a single hungry hippo. Which is that one thing that we found was in order to so if we go back to this recall example from before, so you get to the end of the sentence, you see Michelle. Now you're like, okay, I need to see what things are kind of associated with Michelle. And in this case, we're going to, at the beginning of the sentence, we said President Obama. So we're going to say, okay, Michelle, President, there's some sort of relation there. So what we did is we took two SSM layers. So that's why it's hungry, because there's two of them. And we have one of them, we kind of gave it a representation that can kind of say, do a little bit of comparison nearby in the sequence. So it just gives you enough ability to say, okay, I'm going to say Michelle and compare it to the words nearby or other words in the sequence. And then the other hippo is kind of doing that memory thing. So that other hippo is kind of remembering words from the entire sequence. So between this first hippo that can kind of say, do this comparison, and then the second hippo that is remembering words through the whole sequence, then you can say, you get to Michelle, and then you can say, oh, there's a president that appeared some time ago. So now we can bring out Obama as the next word. For those who are listening who are kind of more technically inclined, there's the way that the physical mechanism that we use, it's called a multiplicative gate. All that means is that we take the outputs of these two hippos and we multiply them. And that's kind of how we do the comparison.
Yeah, it's part of it is inspired by attention. Of course, attention, you have tokens interacting with each other. I think this gating idea actually goes a while, go back a long time to even in RNN, things like long short-term memory LSTM. They were doing this kind of gating. So people working in recurrent neural nets were thinking about these things, I guess, 10 years ago. More recent stuff on state space, I think there are folks at Google who are thinking about this kind of multiplicative interaction as well. I think there's concurrent work from Sasha Rush group. Actually, we've been chatting with them, exchanging notes. So we see that, hey, this multiplicative interaction actually makes it work well for both language modeling, causal language modeling, which was what we were doing, and they were working with mass language modeling like BERT style model, and they also found that this multiplicative interaction is quite helpful there as well. So I think some of these old ideas are coming back and becoming useful again. So that's like more on the modeling side. I think the other side is this efficiency side, which is like we see that these models, if you want to scale them up to be large, that's actually really expensive to do. And if you don't have the right framework, if you don't have the right kind of optimization, it's actually really hard to do. So we've been working hard to make these things efficient so that we can scale to relatively large models. And of course, we want to scale larger given budget. But I think, thinking about like taking some of the ideas from the existing literature on kind of expressivity, multiplicative interaction, combined with improvement in efficiency, I think is what enabled us to do some of this work.
Hey Tree, question for you: how do you measure the expressivity? Like, what was kind of your way of comparing across what this was doing across these types of data sets? Like, how'd you measure that?
Right. Yeah. So you can measure them through performance on the task that you care about. So for example, nowadays people do language modeling and they measure either complexity, which is a metric on the upstream pre-training, or measure the zero shot or few shot evaluation on downstream. That means like, how well can you prompt a model with some examples, and can it then figure out? This is called in context learning. So that's pretty expensive to evaluate. We have some of that. I think Dan can go into more details about some of the toy tasks. One of them he mentioned already. Some of the toy tasks that we figure out so that we can kind of along the way design better model. So Dan can go into more details about that.
Yeah. So as Tree mentioned, one way to test is just train a big model, wait a week, then at the end see if it works. But that's a very expensive way to do research. Maybe at certain nameless large tech companies that have too many GPUs and other hardware, maybe that's something you can do. But as a couple of grad students, it's not something that was quite available to us. So we put some effort into developing these kind of toy tasks. So Jason, you mentioned the recall one. The toy task is kind of, you go even simpler. You come up with a fake little language that has, 10 words in it, and then you give it a little bit of a pattern. So one is called associative recall, and you just have, some words be keys and then some words be values. So an example is like A, 3, B, 2, C, 4, D, 1. And then you say, okay, A, and then you have the model try to predict what comes next. And so this is kind of a very toy version of that President Obama, Michelle Obama in the park type thing. And that's a task that you can run in minutes on your computer. And then we were finding that the S4 and some other things just by themselves before H3 were kind of having a lot of trouble doing that. But then when we designed H3, we saw that it could kind of pick it up immediately. And then that gave us the confidence to then go start the expensive runs, do the big downstream evaluation.
I gotta say, I love the examples you've been giving, Dan. They've been super helpful.
Thanks.
I wanted to ask just if you guys could talk a little bit about the results, because the results that you mentioned in the paper are very, very impressive, both for your kind of pure H3 language models and then also the blended one where you throw in like 2 attention layers. Just curious if you could say a little bit about that.
Okay, yeah. So I think in some of the large benchmark tests, we saw that just pure H3 does almost as well as transformer. There's still a little bit of a gap that we want to figure out. I think transformer and attention in particular are doing something pretty powerful, and we don't completely understand all of that yet. So we make a step towards understanding what transformer is doing. Can we achieve the same thing with a different architecture? And as you mentioned, when we mix it with one or two attention layers, we saw actually really promising results. So on some of the larger language tasks, we saw that this hybrid architecture does as well or slightly better than transformer. And that's really encouraging because transformer has been an architecture that's been there for 5-6 years. If we want to let's say scale along a context and figure out something that does about as well, but maybe scale better. So we were able to get some results models upsize up to, I think, 1.3 billion and 2.7 billion language models that does about as well as existing transformers like GPT-Neo. So that's pretty encouraging, and we're excited to either scale that up or figure out a way to do even more efficient inference. I think inference right now is a big concern for most folks who want to deploy these things, and we believe that state-space methods could be much more efficient during inference. So we haven't done as much work optimizing the inference, but we already saw some early promising results to show that, hey, these things can do inference quite a bit faster. So that would be fun to push on, either scaling things up or optimizing the inference piece.
I had two quick kind of related follow-up questions. One was, does this blended architecture where vast majority of the layers are H3, but then a couple of them are just plain attention, do those have the same long context scaling properties? Like, do you lose the long context scaling properties if you add in just a couple attention layers? And then the other question, which is kind of related, is it's interesting that you get you get a major boost in performance just by adding in a couple attention layers. It kind of suggests that the attention is like doing a little bit that's missing or something, or it has a little bit of capability that isn't afforded purely by the H3 or the state space model. So I was just kind of curious if you have any super high level intuition for maybe what the attention might be doing. It's more high level vague question, but
sure, I can take this. Yeah, so I think one question is what are the remaining attention layers doing, and then can go into more details. We don't completely understand, so that would be really fun to figure out. This is also a call to the community. Can we figure out, hey, we kind of reduce it to just a couple of layers of attention. Can we go figure out what's going on there? And there, the folks at Anthropic have been doing amazing work on the mechanistic interpretability of these attention layers. So hopefully, we'll soon figure out what these attention layers are doing. Now back to the question of when do you lose the long context scaling? To some extent, you don't. In this, so for example, if you have 30 attention layers and you scale context length to much longer, you have to kind of pay the cost for all of those 30 layers. But if you only have 2 or 3 attention layers and you scale up really long, you only have to pay the cost of long context for two attention layers. So it's not so bad. Ideally, we would figure out what these attention layers are doing, and kind of replace them with alternatives, and then can go into some more detail, some of our deeper dive into what we've been playing with.
Yeah. So Tree is mentioning or referring to a couple works that we actually don't have out yet, but we'll be releasing probably in the next couple weeks. But we did some deep dives into exactly kind of what these remaining attention layers are doing. And we found that maybe it's possible to kind of remove them. So one super simple idea that we had that actually somebody, one of our lab mates named Michael Pauly came up with was just we mentioned H3 has these multiplicative gates, and he thought, okay, I'll just add more. And when he did that, he was able to start seeing some kind of initial promising results of language models completely without attention. So we're very excited about that. I hope we should be seeing that come out within a couple of weeks. We also poked around ourselves, kind of did some interpretability explorations. One thing you can do is you run a sentence through your model, and then you say, okay, in the attention that the attention that happened, it's kind of doing this brute force comparison. You can say, okay, which things is the things that's more similar or less similar, and there you see some patterns that we were able to kind of look at and kind of get some intuition about what's happening, and then some of these follow-up works that I think you'll be seeing pretty soon. We were able to kind of take some of this intuition and play with it.
And I guess from a pragmatic point of view, I guess attention is still, is doing great things, right? It's powering all of these exciting applications. So, it's here to stay. Like, we're not saying like stop all your transformer training. No, like if it looks great for you, it looks great for you. I think we're more curious about, hey, one, understanding what these things are doing, to what extent can we replace them? And two, what are some of the new applications that maybe we need to go beyond the quadratic scaling of attention? So, yeah.
One maybe high level question for you guys is, any idea of, I feel like a lot of product people, listeners who, fans of AI right now might be curious, what are some product applications to what you all are building? And how could someone leverage the blended architecture you came up with and, and take advantage of kind of the long range kind of tasks? Any examples of kind of product applications of this?
Yeah. So there's, I think, a couple that I'll speak to a couple that we know of because people have sort of reached out to us. One I think that we've mentioned a couple times is code generation. So you're writing a code file and you have some import at the top, and it's kind of very important for your code to work in kind of very important context. But you've written a very long code file and you're at the bottom. So your Copilot or whatever the next version of Copilot could be, it would be useful to kind of look at that, be able to have that context. Or I think, as Tree mentioned, maybe you have a file and you have a piece of code in another file that's very relevant. Or maybe there's like some comment somewhere in some other part of your code base. So code generation, I think, is very compelling. Video processing, video understanding is another one of these, where your average YouTube video these days is probably like at least 10 minutes long, 60 frames a second. That's thousands and thousands of frames, way longer than anything than a transformer can process these days. People have talked to us about biological applications. So one of the longest sequences that we deal with on a daily basis is our DNA. I won't go into the details of biology so that I don't embarrass myself with my high school biology understanding, but there's a lot to do there, kind of with understanding the genetics and the genomics. So those are kind of three examples that we're very excited about, that people have talked to us about. But I'm sure that there's many others.
Yeah, and I think there are these new AI workflows that are much more interactive. So ChatGPT, as I mentioned, you go back and forth with the chatbot. A bunch of companies are building kind of AI assistant, AI teammates that you go back and forth. You ask it to do something, and then it'll take some actions, and you can either correct or accept these actions. So these multi-turn user interactions going to be really important. There are folks building things like automatic like slide generation, like kind of a remote worker. You ask them to like, hey, make 10 slides on this thing, and it would go make 10 slides, and then you would go back and forth and give feedback. And it's kind of amazing that these folks are building these things. I know of one where it's like one or two students spending a couple of weeks, and they can build pretty compelling applications. So these things are going to be everywhere. They're going to require interaction between users and the AI system. So I think this kind of long range context is going to be more and more important in the future for these AI workflows.
Fantastic. Well, thank you so much. The last question I have is for those who are listening, where can they find more about what you've been working on, and where can they follow you for future research updates?
So for H3, we have our paper online. I think if you Google Hungry Hippos Stanford, it should get down to it. If you just Google Hungry Hippos, you'll probably get the board game. Or I'm not quite sure it counts as a board game, but you can read more about there. We have some blog posts. The code is up. I think probably the best way to follow future research is Twitter. Apparently that's how research is done these days. So we're both on Twitter. My handle is at RealDanFu. Trees is, I think it's tree_DAO, if that's correct. Yeah, so those are, some ways to find us. Of course, we're academics, so we go to all the conferences. So H3 will be at iClear in Rwanda. So if you're there, we'd love to chat.
Great. Well, great to meet all of you. Great to have you on. Love the work, and hopefully we'll run into you out in the conference circles or something.
Yeah, thanks so much for inviting us. It's been really fun.